So here we have a very sparse template to start with. We're going to create our A matrix, which is going to be 25 by 25, and then our B vector 25 by 1. And once they're created and filled in, we'll be able to solve for the unknown temperatures. If we go back to what we're looking at now, though, is building up the A matrix. So it looks like this construction here. We're going to use our guidelines that we built up on this page, though, to actually compute what's happening here. So we're going to focus on the -4 down the diagonal first. So what can we do with that? Perfect application of a loop. We're going to have I equals 1 to 25, and A in that row and that column equals -4. So we'll save that. And what that should do is loop us through when I is 1, 1, 1 will be -4. Then I is 2, at 2, 2 we'll put a -4, and so on. Let's run that to see what happens. And we'll also open this viewer just to be able to see what we're looking at. So that has correctly put in -4s all the way down the diagonals. Of course, that wasn't quite what we wanted. It was close, but not quite. We need to have -3s at T1, 6, 11, and so on. Well, that we can clean up after the fact. So we put -4s everywhere first, but rather than having a complicated if-then thing, we can put the -4s, and then afterwards, we can just overwrite the ones we want. I'll show you the example here with the -3s and explain the logic. We now have -4s everywhere, but now at 1, then count by 5 to 6, count by 5 to get to 11, all the way up to any time before 25. That will give us the -3s at the specific locations we itemized here. Fill them all with -4s, then overwrite some elements with the -3s. Let's run that and see what happens. Take a look at our A. Perfect. -3, 4, 4, 4, 4, 4. At 6, we have a -3, 4, 4, 4, and we can keep checking, but the logic there was pretty solid. All right. Now the off diagonal. There's other ways, of course, to arrange all of this. This is just one way to structure the loops. The key thing is at the end to have these features in our A matrix and B vector. Let's go for the above diagonal and below the diagonal. All ones. We can take the same approach we did before, except for some elements. So let's do the all ones first, and we'll see that. So I'll have 1 to 24. It's important not to go too far here, because once we go off the diagonal, we're not going to need to go as far. Let's try that. So we're going to go through row 1 down to the second last row, 24, and to the right, so the next column over, we're going to put a 1. What does that match? That matches cell 1, 2, perfect, 2, 3, 3, 4, all the way down to the last row. Well, we can't actually put something in the last row because that would lead us into column 26, which wouldn't make sense. So we would do this last in row 24. Oh wait, row I 24, column 25. That works out perfectly. Let's run that and check our A matrix. Lovely. 1's all the way down, and it's still a 25 by 25 matrix. However, we do need to put some holes in here. In row 5, 6, we want to put a 0 in there. So let's replace those with the 0s in the off diagonal every 5 elements. Again, several ways to structure this, but let's go 5 by 5 to 24. And when we do that, we'll want the A at I plus 1 to equal 0. One handy shortcut in Windows, Control A to select everything, Control I auto indents everything so you can see how your loops are working. And that should start at row 5, make the connection between cell 5 and cell 6 a 0. Let's run it. In row 5, column 6, we have a 0. That matches what we wanted here. In row 5, column 6, we wanted a 0. And that pattern would repeat further down because of the way the geometry was laid out. Now we actually want to do exactly the same thing in the subdiagonal, and we could do it a couple of different ways, but it makes sense to leverage what we already have here. This is the upper diagonal, but we can also do the same thing for the lower diagonal. Take the row plus 1 and the column being I. And just to confirm, that would start us at I is 1. That would be cell 2, 1. Cell 2, row 2, column 1, perfect. Then row 3, column 2, row 4, column 3, perfect. And the same thing would actually apply equally for the lower diagonal for the zeros as well. Fingers crossed, let's run this. We still have a 25 by 25, that's good. We have the 1s now, and then a 0, 1s and a 0. And on this side, it is at T6, row 6. We have a 0 in column 5, because cell 6 is not connected to cell 5. But then they come back to 1s after that. Lovely. That is 2 out of our 3 patterns taken care of. The only thing left actually is this real off diagonal element here, where we start at T1, T6, but we've already seen the kind of pattern that we can work with on that one. And that would be I equals 1, 2, we can't go too far, it'd be up to 20, 5 less than the total, because we're off by 5 rows or 5 columns. And then A at I plus 5 equals 1. I'm going to do the select all, indent everything to make it pretty, and that's our new row. This is the off diagonal. We're going to save that. We'll run it and take a look. Lovely. Here's our 1s starting at row 1, column 6, row 2, column 7, row 8, perfect. And this one we will scroll all the way across to, we should see, there we go. Row 20 is connected, or cell 20 is connected to cell 25. If we take down our diagram here, this is cell 20, this is cell 25, there's a connection between them. Perfect. That's all of these ingredients up here, and it's exactly the same pattern in the off diagonal to the lower side. We can actually use our same code again, just with I plus 5 here in the row I. So this takes some practice, takes a little bit of connecting the on-paper work back to the MATLAB work. Do pause the video as you need to get the associations, but that is going to do what we want. I'm going to run that one more time, check the A matrix, and sure enough, there is our lower diagonal. I just saw it there for a glimpse. Here, we start row 1, or column 1 is connected to cell 6, and so on. Every non-zero element in here corresponds to a connection between this cell number and this cell number. So 4 is connected to 4, no kidding. But 4 is also connected to 3, 4 is connected to 5, but 5 is not connected to 6. All of those patterns in the geometry are reflected in this matrix. Now, last but not least, we still have the B vector to do. Parts of it are easy. We know that in our calculations, we had minus 20 for the T1 to T5. So we know how to do that now. Here it's a vector, so we'll just use single indexing. And that will actually get us the first bit of the B vector. We also have a pattern for the second part, which is T5, T10, T15, up to T25. So counting by 5s, we're going to have, starting at 5, counting by 5s up to 25, we're going to have a negative 120. I'm going to pause there for a second, and we'll run that. Now the challenge, we can take a look at the B vector here. The challenge is that this value is actually negative 120. Well, why is that bad? The reason that's bad is because at T5, we're actually supposed to get an accumulation of the negative 20. Let's look at our cell here. T5 is connected to the 20 degrees and it's connected to the 120, and we need both of those effects for a net total of 140. So we have to be a little bit careful about this, but we can go back to our code and recognize that what we did here was set the value, force it to be 20, but here we also forced it to be 120 regardless of whether we had set it before. Well, how can we get around that? We can just make the change relative. In other words, whatever value was there before, subtract 120 from it, most of them will be 0, so we'll end up with negative 120 anyway. But if there was a value there before, say in cell 5, we're going to get an accumulation of that before we store the value again. And if we run that and check our values, we're going to see, hopefully, yes, a change there. Negative 140, whereas all the other cells that haven't been touched yet all have negative 120s, which is exactly what we want. And the last thing we have to capture is from 21 to 25, counting by ones. We'll do the same relative change, take the value we have now, and subtract 100. Look at the B, and we haven't run it yet. That's why we haven't seen the change. Let's run that. And we see indeed negative 100, 100, 100, negative 220 for the last cell, and that corresponds to T25 down here being adjacent to 120 and 100, and a coefficient in the B vector of negative 220. So that's a bit of a whirlwind going through all of the construction of the A and the B vectors, but we have faith that that's done correctly, and we can associate everything that we did back to the connections in this diagram. This is the source of all the definitions, all the relationships. Just like in a truss diagram, the equations all come back to the geometry in the truss itself. The last step is to calculate our answers and interpret the results. So let's run this again, and let's take a look at our t-values. Here we have a lovely long list of t-values. We're going to copy and paste those over, see what those look like. All right, they're a bit bulky here. Let's see if we can squeeze them somewhere. That might be as good as it gets. We'll put them here. Once that's been computed, we can translate the values back. This is T1. That is T2. And if we go down 3, 4, and 5, we see a little bit of a jump as we get to T6. So if we put these in rough order, 38, and just rounding to, that would actually be a 40, 44, 52. Actually, this is already complicated. As soon as you find yourself repeating an activity, it's probably worthwhile simply changing the way you're approaching it. And let's print this statement using 0 decimals and our t vector here. And what we'll do is put a /n at the end. There we go. That'll be a lot easier to read and interpret, and it'll do the rounding for us. So we'll just erase those. There we go. There we have our temperatures a little easier to see. 38, 40, 44, 52, 71. And then the next row, sorry, that's 71 is the T5, and T6 is the 55. 57, 63, 73, 91. All right. So what we see is this plate here is sort of doing its job. Good, we've done our math correctly. That this temperature here is sort of in between 20 and 120 degrees. But it's not perfectly in between because there's other effects from the cells nearby. We do see that these temperatures are relatively cold, but we see temperatures going up as we move down to be adjacent to the 120 and the 100 in the long run down here. At the very end, we would actually have a temperature of 106, 99, 95, 92, and so on. 91. The key thing being we can lay out all of these temperatures that we computed into the grid and tie it back to the original diagram so that we can say, does this make any sense whatsoever? Gosh, that was a lot of work though. Wouldn't it be nice if we could just have the matrix lay itself out the way we want it to? And that's what we're going to do here. There's a reshape command. As you might expect, anything you think you can do in MATLAB that you would naturally do with a matrix is probably built in. And that's exactly what we have here. What we're going to do is add that. We're going to calculate our t's, then make a t matrix, which is reshaping what we have already into a 5 by 5. And for reasons we'll explain in another video, we have a transpose. And here, actually, we don't even need that. Let's just comment that out. And we'll run that. Now what does TM look like? It looks like that. This time it's already laid out, so we might as well grab that in its current form and paste the values in, make it wide enough so we can see the structure, and away we go. We have all our temperatures, and we can actually now do some pretty simple verifications. We can verify that the temperatures are in fact the averages of their neighbors, and that the temperatures along the edges are close to the 20, 120, and 100. Might as well do that here as well. Makes it a bit larger to start with, and paste. There we are. So we can see along this border here, temperatures around the 120, or at least adjacent to 120. A bit cooler on the inside because they're distributing heat inwards. The temperatures along this side certainly seem on the range of 100, except for this one in the corner, because it's being heated up even further by the 120. And yes, cold temperatures along the top, and a fairly even progression along here, because we have that insulated wall that has no temperature effect along this left-hand edge. So what we're seeing here seems entirely reasonable for a way to handle this kind of temperature distribution. So not bad for a lot of theory, but essentially 40 lines of code. And we're actually going to see that this is even more powerful because we can turn that 40 lines of code into higher and higher resolution images of this same plate with a small tweak. For now, though, it's a pretty big success just to be able to compute the equilibrium steady state temperatures on this 5 by 5 grid for this steady state temperature distribution.